Hello, Adisheshu.
Hello.
Yes, sir.
Yes, sir. The question is, according to Prendel's lifting line theory, a very
Okay.
good approximation of flow field
Okay.
over a finite wing can be
Hmm.
modeled by
Hmm.
dash, and the hint is given. Think only about the wing and not its wake.
According to the, can you repeat the question once again? Is it an assignment
Sir,
question?
yes, sir. Assignment was means due date has been passed, sir. I have means the answer was incorrect. Means I just ticked horseshoe vortex, but the answer was bound vortex. Therefore, I want to know the reason for the answer as bound vortex. Why it is bound vortex?
Okay. Can you repeat the once again? According to the Brandel. Sorry. Can you repeat the question once again? According to the,
According to Prendel's, yes, sir.
let me say
According to
it.
Prand,
Which uh, assignment it is in?
sir,
It
week
is in
four.
week 4.
Week sorry, sir. Not week four. It is in week five.
Okay.
Week five, question number 9.
Week 5, question number 9. Just a minute. I am looking at it. Week 5. Its assignment is done, right? Is it
Yes,
already
sir.
open,
Yes, sir.
the assignment submission? Okay, assignment submission is
Yes, sir.
open.
Yes, sir.
Week 5, question number 9. According to the Brandel's lifting line theory, okay, a very good approximation of flow field over a finite wing can be modeled by dash. Modeled by dash. And the answer they given is bound vertex.
Yes, sir.
Think only about the wing and it seems like your horseshoe vertex is the correct because of finite wing. Um, we generally model with a finite wing only, like the horseshoe vertex. With if you want to model any lift over a
Yes, sir. Sir, actually, I ticked horseshoe vortex option only, but the answer came as bound vortex. That's
yeah.
why I just wanted to clear my doubts, sir. Why it is getting bound vortex?
Okay, I will just clear with the professor, or I will ask the concerned person. Like for me, also it is like horseshoe vertex, or if it is out of my knowledge, like why the exact answer is coming to the bound vertex they mentioned, or if by mistake it happened. But up to my knowledge, it is the horseshoe vertex as your understanding is. So I will re-verify and let you know with the team.
Oh, okay, sir.
Okay, if it is like if I'm not aware of this, I mean the answer, like if there is some other logic they given to this, I will learn from them and I will let you know.
Okay, sir. Sir,
Okay.
actually, there is a hint given. The hint
Yeah.
is given that think
Think
only about
about
the wing and
not its the weight.
but
Yes.
yes, sir. From
Think only
that,
about the weight.
I was not able to model that question, understand that
Okay.
question.
But if you want to model good approximation flow over a finite wing, it's is they're asking it's completely finite wing. It cannot be bound vertex. Like they're asking for the complete modeling of flow over a finite wing, right? Bound vertex place. Bound vertex is there. It's like if you cannot model
Yes,
with the
sir.
bound vertex over the flow and entirely on the flow over the airfoil, not entirely on the finite wing. It's a airfoil. You can think of modeling with the bound vertex, but in the finite wing case, it's not about the bound vertex. Okay, I will let you know. I will write this question and I will forward to them.
Okay, sir. Okay, sir.
Maybe if you can post this question in Google Form, I can answer you better once I know the whether it is by mistake or any concept is hidden behind this.
Okay, sir. Sir, actually, from that video, I came to know that
Hmm.
Prandel's rifting line theory was basically modeled using horseshoe vortex only.
Yeah, yeah,
So therefore, I take horseshoe vortex according to my knowledge, as per
yeah.
my knowledge.
If you are like see in any basic aerodynamics books, like the finite wing, it's two different concepts. Infinite wing is one thing, and finite wing is one thing. So finite
Yes, sir.
wing, the basic idea is modeling with a single uh, vertex sheet and the form of a horseshoe vertex. Are you able to understand my terminology? Like it's a single vertex sheet
Yes, sir.
deforming into a horseshoe kind of vertex. Yes.
Yes,
So
sir.
I'm noting down this. Question number 9 from assignment 5. Week assignment 5, right? Yeah, assignment 5. Thank you, Arhit. I will mention to them. Also, please,
Thank you, sir.
please post this in Google Form so that I can reach you once I get update of
Okay,
it.
sir. Okay.
Okay. Okay. Thank you, Arhit. So, any more queries from anyone in the meeting? Let me see who else. Okay. So, with no queries, we can proceed for our today's session. Today, we are continuing with our discussion that we left in the last week.
Sir,
And yes,
uh, sir, another thing I want to means ask you that, sir,
yes.
these questions are not posted by the NPTL team uh, in my mail, means that
I'm
out
not.
clearing session you conduct.
Are you able to see these things? I mean, are you not able to see these things in? Let me show. Let me show you. If you go to the your account after login into the course outline content in the course outline, there is at the bottom problem solving session. Can you see that? I just opened in another system. I cannot share you the screen.
Yes, sir.
In the course
Yes, sir.
outline, you can go to the problem solving session, and in that problem solving session, you can see this click here for the problem solving session lectures.
Sir, only one video is only given. That is of Professor Arnab Ray's video. But
I
none of your problem solving session is posted, sir.
Are you sure? Problem solving sessions. I'm able to see like all my YouTube lectures in that last past 4 weeks content. Can you share your screen? Is it possible from your end?
Yes, sir. Yes, sir. I am sharing.
Yeah, please share.
Sir, here it is written only meeting organizers and presenters can share.
Okay, meeting organizers and presenters. Okay, let me try to log in here once again and I will show it to you. If that is not the same case to you, and is it recording? Yes. I will ask them to find out the problem. Like for me, it is showing. Let me share my screen once again. So are you able to see this?
Yes, sir.
Yes. In this problem solving session, uh, problem solving session. Can you able to like in your account, you are also seeing the same way or different?
Yes, sir. Just let me check once.
Yeah.
Hello, sir.
Yes. Who is this? Yes, Adisheshu.
Sir, can you explain me the sixth question in week 5 assignment?
Which week?
Fifth week assignment. Sixth question.
week assignment. Let me see. Sixth question. This one, right? The
Yes,
direction
sir.
of the
It
flow.
has been posted. Yes, sir.
Are you able to see all the lectures, YouTube past YouTube lectures, right?
Yes, sir.
Yeah, fine. So sixth question, the direction of the flow that crosses the top surface of the wing is that crosses the top surface of the wingspan is. It's from perpendicular to the wing surface, from wing tip to the root, from root to wing tip. You understood this flow over the like the downwash concept, or like upwash and downwash kind of concepts.
Yes, sir.
You are sure? Like
So
I will,
actually,
yeah.
that one flow from leading edge to trailing edge, sir, or
Mm. It's not, he is not asking from leading edge to trailing edge. He is just asking how the flow will cross uh, on the wing, whether it crosses along the span from wing tip to root or root to tip. It's they are asking about the wing. So wing means let me clearly draw the picture and I will show you. Okay, are you able to see this PPT?
yes, sir, yes.
Okay. So if you see a airplane wing, I'm not able to draw very neatly, but kindly adjust with me. If you see aeroplane wing like this, so this is your wing, right?
Yes, sir.
This is the flow you are able to see. So wingtip vertices, the possibility of performing the wingtip vertices is from root or the tip.
From tip.
From the tip, yes. So from the tip, the flow will move like this because of this wingtip vertices. Okay. After forming
Yes,
of
sir.
this wingtip vertices, this flow moves towards the root.
Root.
So tip to root, that is what they are asking.
Yes, sir.
You
Thank you,
got
sir.
it? Okay.
Yes, sir. Yes, sir. Thank you.
Yeah. So Adish, not Adishish, Adishish, your doubt is clear. Arhit, your doubt is also clear. You got the things. I hope you got
Yes,
the
sir.
things.
Yes, sir.
Okay, fine. So let us go to start our session. Any more queries? Okay, if no queries, we can start the today's discussion. It's not operating. Okay, welcome to the session once again. Today we will see the week 5 content, and I will just give you a quick overview of the things that we seen previously. Uh, Sorry. So in the last week, we understood about the substantial derivative. The substantial derivative of any parameter, whether it's a flow parameter, pressure, velocity, density, or temperature, you can write the substantial derivative of that variable in this format: d capital D rho by capital dt equals to u. These are the parameters that is necessary. The velocity field is necessary for that convective acceleration or convective rate of change of that parameter. These three terms indicates the convective rate of change, where the fourth term indicates the local or a temporal rate of change of that parameter. The formal, this is the formal equation format of that convective of that substantial derivative. So, and then we discussed about flow over an air, any bluff object, bluff body, or if there is a bluff body, and we defined a particular term called a non-dimensional term, that is a Reynolds number, which is the ratio between inertial forces and viscous forces. And the characteristic length is the key length parameter that deciding the physics of the flow over that body we need to take. It is up to the user or experimentalist concerned, like which parameter he is going to decide. He needs to justify what is that characteristic parameter. And then uh, the x momentum equation we see now, which consists of viscous terms also, which is very important for solving the fluids, real-time fluids within the laminar case. We are not still entering into the turbulent cases. For the turbulent cases, the equation terms are a bit different. So in the turbulent cases, you can see if you want to, there will be a fluctuation term, so that those things we can delete later. And we can see in this momentum equation also how this Reynolds number is playing very key parameter. This is this parameter rho infinity c u infinity by mu. This is the formal equation of non-dimensional parameter that is called Reynolds number. So it is playing a very key role. If this Reynolds number is going to infinite, your flow behaves like a inviscid kind of fluid. So this is very important parameter. So if it is very low value, you can see very high dominant if the Reynolds number is in 1 by RE, right? So if you have very low Reynolds number, the flow field behaves like highly viscous, and drag forces on skin friction coefficients are very high. And any 3D inviscid flow that we discussed like in the last week, if you have any 3D inviscid flow, it's not only for the 3D inviscid flow, but also uh, viscous flow also. One can write a formulation like del cross V, that is called vorticity. We already seen the formal definitions and derivations of that in previous lectures, and that is del cross V, how this gradient also can be identified, or that based on the determinant of velocity field and this curl of the velocity. And we also have the Euler's equation that is basically derived by taking the this you need to memorize, or you need to keep in your mind all the time. This is a short definition, like your dp is equals to rho v dv, but this is very important for your entire course, like how it can give you the beautiful meaning, like it can apply for uh, both compressible and incompressible flows. You just need to integrate for your respective application. And here you also have, it is first started with the inviscid flow only, but it includes the formal definition of del cross V bar. So the inviscid flow, you have only left hand terms, the convective terms, or the advection terms. On the right hand, you have the pressure gradient terms. With that understanding, we started this derivation of for Euler's equation, and we ended up here. After solving the or obtaining the Euler's equation, if we state some more assumptions, like if the flow is irrotational flow, or if the flow have, like if you are investigating your flow only along the streamlines, if you are measuring the properties of the flow only along the streamlines, or some other special conditions, then you can get a very famous equation called the Bernoulli's equation, um, which can be applied for the incompressible flow. There are Bernoulli's equation for the compressible flow also, but we are not going to discuss here. And then the compressibility, how we define the compressibility is, it's a rate of change of volume per unit volume for the change in unit pressure. So that is how we define the compressibility, and it sometimes people denotes with a K, letter K, or sometimes denotes with the letter tau. And here the compressibility definition why we mentioned is, we just discussed what is Bernoulli and what are its condition. The condition is the flow field should not be compressible. So as a engineer or as a scientist or whoever wants to understand what is the compressibility and incompressibility, and we already applied the condition, but we should know what is the compressibility or incompressible fluid. Uh, for that perspective, the compressibility means if there is a change in density in the flow field, which is moving at low velocity or high velocity, but if the change in density is more than 5% of the local density, or the initial input is more than 5%, then the flow is considered as a compressible flow. So it should be always keep in mind for what or like why we are using this compressibility flow. It is very necessary for our understanding what how we are differentiating the compressible flow and the incompressible flow. So then we discussed about, I think it's a doubt concept asked by one of the student, and one of the students like he asked how to calculate the moment coefficient about the leading edge. In the today's problem session, Professor Arnav Roy also discussed how to calculate the moment coefficient about the leading edge, and how moment coefficient and lift coefficient combinedly uh, gives a different understanding of studying the airfoil concepts more detailedly. So, and then we discussed the continuity equation in integral form, and we applied it for one-dimensional uh, kind of problems. And then some sign convention also we followed using these. We get that a1 v1 equals to a2 v2, which is known as a very basic kind of fundamental equation in the basic level of fluid mechanics, which is a continuity equation in one dimensional. A1 v1 equals to a2 v2, where area and even the area and velocity uh, between 2 points, but the conditions or the reason, assumptions behind this are very vast. So we need to carefully apply this equation. So if there are some experimental or real life situations where we can use this equation without any significant lose of error, significant lose of accuracy in the data, then we can also apply this equation in the Bernoulli equation. Once you apply this in Bernoulli equation, you can get a format of stagnation pressure and the relation between stagnation pressure and static pressure, like how the stagnation pressure in the incompressible flow is converting to static and the kinetic energy. So this is then also an important relation that one should understand the derivation also. And then we discussed based upon that static and stagnation pressure. Uh, Instead of dealing with absolute values or dimensional parameters, it is always encouraged, or it is always a common practice of aerodynamists, like they used to do with non-dimensional parameters, with like the pressure coefficient Cp. So if you have a pressure coefficient Cp, then like not Cp, if you have a pressure on the aerofoil, like at a point A or point A and point B, and because of this point A, velocity at the point A, static pressure at point A, because of the properties at point A, which is nothing but the free stream, where uniform flow field is coming on to the aerofoil, you will see changes in pressure, velocity, and flow features or flow properties on top of the aerofoil. These properties are governing by the Navier-Stokes equations, the momentum exchange, momentum conservation, and mass conservation. So a very common definition that we always use is a pressure coefficient, that is Cp is equals to P minus P infinity by half rho infinity square. And you can also include that using the continuity equation, that is a1 v1 equals to a2 e2 for one dimensional form. If you can include that one also in the Cp definition, one can also get that Cp equals to 1 minus u by u infinity whole square. So this is also a formal important definition of obtaining the Cp. I think you already covered this in the lecture sessions, but it is just a recap of all those things. So if you have followed all the lectures detailedly, that the application or uses of this Cp equals to 1 minus u by u infinity square, you have already seen in flow over the aerofoil or thin aerofoil theories, calculating the pressure coefficient in a derivational sense. So you might have already gone through those lectures for your better understanding also. Then we also discussed what is a uniform flow and what is the Laplacian equation, how it's formed, the Laplacian equation, what is the velocity potential. These kind of things are all discussed here. Now we will see today uh, let me take my pen. Okay. Okay. Can I use another? Give me a second. Now let us see today uh, a few more remaining concepts of from the last week. This session is been recording. We are today seeing that laminar boundary layer, and we did not start this laminar boundary layer in the past classes, but we stopped at the uniform flow, where the uniform flow and all the primary flows like sink, source, doublet, vertex, point on this point vertex, all the things already covered in the past lectures. You can go through that, and this is just a recap of a previous lecture as we are going a bit review kind of way, and we are solving the some problems. Let's see the boundary layer equation. Suppose if you have a flat plate like this, if you have a flat plate like this and the incoming flow is a uniform flow with the velocity of u infinity, you can easily see, not visible by naked eye, but from the observations, one can find out there is a formation of the boundary layer. For a laminar flow, laminar boundary layer, this is the approximated velocity profile, or one can measure also. This is the format of parabolic kind of velocity variation within the boundary layer. And within this boundary layer, you can also see u equals to 0.99 times of u infinity. Like at this point, if we find the locus of all these points in the y direction, suppose this is your x direction and this is your y direction, measure the velocity from bottom to like at every point. If you go, the velocity varies with like this r vector, and the point at which your velocity is approximately equals to, sorry, approximately equals to 0.99 times of u infinity. At that point, we call it as a boundary layer thickness. So in the boundary layer thickness, the governing equations can be further simplified. It was actually found out by Ludwig Brandel boundary. We say this Ludwig Brandel boundary layer theories. Like for a incompressible boundary layers, the continuity equation is retains its format dou u by dou y equals to 0. For it is for only for flat plate, and the momentum equation becomes u dou u by dou x plus v dou u by dou y is equals to minus dou p over dou x plus 1 by Reynolds number times dou square u by dou y square, where this is you see is a x momentum equation. And for the y momentum equation says everything will be cancelled out. Only dou p by dou y equals this remains for the flat plate. That is, the pressure gradient in the y direction is 0. Okay, so this is the these are the governing equations of laminar boundary layer. One can solve for the boundary layer features using these equations. We can solve, and the formal solutions also there. We discussed in the, I mean, the professor discussed in the class in a very brief way what are the solutions for these boundary layer equations. And then for compressible flows, actually we are seeing for the incompressible flows, these are valid for the incompressible. For the compressible flows, how it behaves like within the boundary layer, like a large amount of kinetic energy needs to be dissipated. That is because it's a flow is already compressible, so and flow should reach the zero velocity at this location. On because of the no slip condition, it should reach a zero velocity here. To reach a zero velocity, and suppose this is 340 meters per second, this much of kinetic energy or this much of velocity needs to uh, come to zero here within this small layer or within the small bound thickness on the flat plate. So it is sensible, like it is this sense that like if you are having very small thickness and a large amount of energy is going to zero, then so much of energy is going to convert into the dissipation, and also it converting into the heat energy, or it increases the internal energy, thereby as the internal energy is just a function of temperature. So you can see a lot of heat flux uh, on the flat plate or the body, which is having a lot of kinetic energy on top of it, like capsules that are coming from space, or the re-entry vehicles which we see. We can say as the best example of it. And few important glacier solutions for these governing equations of flow over flat plate. The glacier solutions says that shear stress can be written as 0.332 times rho infinity u infinity square over square root of Reynolds number at any x. And the Reynolds number at a point can be defined as, suppose if you are moving in the x direction, and the Reynolds number at this point, that is location x, can be written as rho infinity u infinity x over mu. And the coefficient of the friction, the local coefficient of friction at that point can also be written as shear stress by half rho infinity u infinity square. This is also formulated as 0.664 by square root of Reynolds number at that local Reynolds number. In the same way, if you want the entire skin friction, that can also be modeled by complete skin friction equals to 1.328 times by local complete Reynolds number at the length of the plate. You should use x equals to L at this Reynolds number. So this will give you the total frictional force on the flat plate. And the delta, this is also solution given by that the delta means the boundary layer thickness, that is 5, and the local uh, position, or the local I can say this local position vector, where we need the delta, that thickness of the boundary layer, that is the delta, that is 5x by square root of Reynolds number. Okay, and then it can be seen that the delta is proportional to square root of x. From this equation, the boundary layer thickness is very clearly understandable that boundary layer thickness is proportional to square root of x. One more important concept is that we should always keep in mind that the boundary layer thickness, after that its displacement thickness. Displacement thickness talks about the amount of fluid displaced because of the no slip condition, or because of this viscous effects. A fluid displaces, and a streamline that is uh, moving on the flat plate, the streamline present on the flat plate will get deviated like this. And because of this deviation of the streamline, there will be a displacement of the mass flow rate to the in the vertical direction. So this missing mass flow rate we call, and respect to thickness, it's not thickness means does not represent the physically thickness. It's can be represented as the thickness required by the to compare with the potential flow. In mathematically, it is easier to say in terms of thickness instead of marking it as missing mass flow rate. So that thickness we already formulated based upon the formal definition of missing mass flow rate, or the displaced mass flow rate. That is delta star is equals to integral 0 to delta 1 minus u by uy is equals to dy. This is also known as velocity deficit region. There you have the missing velocity, and yeah, that is up to the boundary layer. Then one more concept is the boundary layer profile is not similar for the laminar or the turbulent fluture. For the laminar case, we just seen how the boundary layer profile is. For the turbulent case, it is more steeper. This is how for the turbulent case you can estimate, like the gradient, the velocity suddenly changes. This is your y direction, and this is your x direction. The velocity at very small region. A very small region itself, you can see a large gradient in the velocity. Velocity changes rapidly in the very small distance. This is not the case in the laminar boundary layer. So in the turbulent boundary layer, this is the important thing that we should understand, that velocity changes very rapidly within the small region, and then it enters into the buffer region and then fully turbulent zone. So this is the difference in laminar and turbulent boundary layer. For more detailed understanding, we can see these things in later course, later lectures. And the pressure drag uh, and the skin friction drag also depends on the type of profile that we are having on the body. Suppose we just seen what is the laminar boundary layer and the turbulent boundary layer. Suppose I have two bodies, one is a cylinder and the flow over it, and another one is an aerofoil and flow over the aerofoil. If I have these two bodies, one is the bluff body and another one is a streamlined body. Bluff body and streamlined body, if you are having these two, and as an experimentalist, you can see the turbulent boundary layer is very steepest, but the shear stress, which induces the viscous effect on the drag forces, is proportional to a gradient dou u by dou y, which is very high for the turbulent case and which is low for the laminar case. So turbulent flow always induces a high amount of drag, but it has a good conditions or good characteristics, like it can sustain high adverse pressure gradient. That means it can retain the flow to be attached most of the time or for the sufficient amount of distance on the body. If the flow is turbulent, it can help to it helps the flow to remain attached within the boundary layer for the longer distance compared to the laminar flow. So that is the reason why we need a turbulent flow on the bluff bodies and laminar flow on the streamlined bodies, because on the streamlined bodies we have um, pressure drag is the dominant. If the pressure drag is the dominant, we need to reduce the pressure drag. So pressure drag can be reduced. Sorry, on the streamlined body, the skin friction drag is the dominant. The skin friction drag is less in the laminar boundary conditions. And in the bluff bodies, the pressure drag is the dominant. The pressure drag can be reduced by uh, trying to remind that by controlling the flow or letting the flow to be attached on the surface for longer period of time. If you can do that, the flow is the pressure drag can be reduced. That can possible by using the laminar flow kind of phenomena on the bluff bodies. So this is the
Hello,
curious. Yes,
sir.
who's,
Sir, I am
who's this?
asking that in case of sir, audit, sir.
Rohit, tell me.
Sir, I am
Yes.
asking that in case of boundary layers, this
Okay.
turbulent flow is more robust and it holds the boundary layer, so that means the flow separation, it does not allow the flow separation to occur easily. Sir, can you just tell why this turbulent flow is so robust, and what is the phenomena which means holds or sticks to the body of the streamline?
Okay. The good thing is turbulent flow has a more kinetic energy compared to the laminar flow. Can you accept it? Like that is a
Yes,
formal thing
yes,
that
sir.
yes, if you have a lot of kinetic energy and but in the laminar flow the kinetic energy is not dominant. The viscous effects are lot dominant here. Okay, so adverse pressure gradient is always trying to stop your flow on the surface, right? Adverse pressure gradient is very severe if you see on a curved side kind of surfaces, not on the flat bodies. Flat bodies, the adverse pressure gradient uh, is not present because that you see already the dp by dy is already zero. So for the curved bodies, you have the adverse pressure gradients effects are very severe that won't allow the flow. Suppose I have a flow here, the adverse pressure gradient dominates the flow to enter in this or to take this curvature. My flow struggles to move on this surface or in the downward direction. I mean, in this direction or upstream direction, I can say. So if it is struggling to move, what I need to do, I need to increase its kinetic energy to overcome the adverse pressure gradient, right? But it is not possible with the laminar case. It is possible with the turbulent case. So in the turbulent case, it has a sufficient kinetic energy and it can overcome this adverse pressure gradient for some time. I cannot say all the time, but some time, for some distance it can handle, and it can remain attached for the some distance because of its high kinetic energy compared to the laminar flow. So you got it?
Yes, sir.
Yeah.
Sir,
Okay.
and another thing I want to ask
Yes.
is the can you just explain that quanta effect?
Conda effect. You are asking regarding the helicopter.
No, sir. Actually, I was searching about this quanta effect. I have not got this from the course, but from my knowledge, sir, this
Conda
quanta
effect.
effect was.
I heard it. It is also looking like. I mean, it's similar to the this effect. I'm not able to read. You know this rotating Magnus effect.
Yes, sir.
Yeah, yeah. I just heard about it and read that Conda effect, but it feels me to like it is more or less looking like a Magnus effect. But with your question, I will just re-look into it about the
Okay, sir.
Conda effect, and I will let you know in the next class.
Okay, sir.
Okay, let me write down that. But once when I read about the Conda effect last time, it made me to think effect which similar to more or less similar to Magnus effect. I will note it down and will clear your doubt in the next session. Give me a minute. Okay. Any more queries?
No, sir.
Okay. Because I can recollect that, but I am not sure that I cannot give you assurance that I can give you the clear idea of the Conda effect. Okay.
Okay, sir. Okay.
Yeah. So any more queries?
How turbulent flow helps in keeping the flow attached to the body?
We just discussed that the turbulent flow has a more amount of kinetic energy. Like, let me show you. We already know that there is a dominance of viscous forces in the laminar boundary layer. Whereas it comes to we go see the turbulent boundary layer, there is a large velocity gradient at the bottom of the or viscous sublayer. In the viscous sublayer only itself, you can see a very sudden jump of velocity or sudden decrease of velocity in the viscous sublayer only in the turbulent boundary layer. And the turbulent boundary layer consists of more kinetic energy, which is required sorry, which is required to overcome the effects of the pressure gradient. Like if the flow is trying to take a turn like this, if the flow is trying to take a turn, it will experience an opposing force, more opposing force from this side. Okay, so this is we say as because it is already accelerated so much up to this point and it is still accelerating to up to this point, its pressure coefficient of pressure is almost at its lowest value. So it is, and its kinetic energy, it is already being like dispersed or reduced because of this boundary layer effect or the viscous effects in the laminar flow. So once if this flow is laminar to turbulent, its kinetic energy is increased because of the lot of fluctuations present in the as every property itself is fluctuates in the turbulent boundary layer, and the kinetic energy also increases suddenly in this way, because you can see here up to this level the velocity is very low, but in the turbulent boundary layer, the velocity is low at very small region, and all the remaining region, the velocity is significantly high. That means it is carrying more amount of kinetic energy, which is helping to overcome the pressure gradient. Are you clear?
It means turbulent flow is good for laminar body.
It depends on your application. Suppose if your application is that you want to use a bluff body like this, if you are trying to apply a body, or if you're trying to your application is placing a bluff body in the free stream. This is the free stream for suppose, and if your application is placing a bluff body in the free stream and you are experiencing more drag force because of this high velocity, you cannot place a streamlined body because the streamlined body has structurally more complications to generate. But for structural rigidity also, and it is not a problem of weight, so you are placing a bluff body like this. But instead of giving more strength, it is also I can say experiencing more amount of drag because of this high velocity, and you have no possibility of placing the streamlined body. At this situation, it is very suggestible, or it is very good if you can create the flow as a turbulent flow to decrease your drag, because the turbulent flow helps to attach your flow on the body for significant amount of distance compared to the laminar flow, so that your wake where the momentum deficit occurs most is reduced. On reducing this wake region, your flow is always, attached up to this region, and increases like it decreases this your wake region and helps to reduce the drag on the body overall pressure distribution. You're clear?
But can the same phenomena can you apply for laminar body? Can you explain how it is dangerous for the laminar body?
I didn't get you. Laminar body means like if you
For
have the same.
for
Yeah.
airfoil, how it is not good?
For airfoil, it is not good. Let me clear you in the new slide. I will take one more slide for you. Suppose you have a bluff body like this, which is a very um, dominant or experiencing the high pressure differences. Suppose if it is a bluff body, the flow cannot sustain or remain attached for the longer amount of distance on the surface. Suppose the distance that you are saying is this way. Starting at this point, this is the ds cover on the upper surface, on the lower surface. So it should start from here, from the stagnation point. So the distance covering by the fluid is the fluid should travel all the way to around the cylinder. For a potential flow, it is not a big case for the potential flow because there we are not considering the viscous effects. But when the viscous effects are severe, the flow starts to separate at some point as it is experiencing like less kinetic energy because of the viscous effect. So it separates some point like this. So when it's separated on the body, the wake width, if you see this wake width, there is a deficiency of momentum. This deficiency of momentum here, it will create a very low pressure also. It's also can create a low pressure zone because the flow is already separated here and it is not covering this portion. Here you can see a free stream pressure. This is a free stream pressure, and this is your deficiency of momentum and low pressure zone also. Because of this difference, as you have difference in momentum also itself, it is very sensible that there is a difference in momentum, and it will creates a it will for the momentum conservation, there should be some force exerted on the body. Okay, so that force we say it as a drag force. Because it is axial also, you can say it as an axial force, so this drag force. But if you see the same thing for an aerofoil, yeah, the aerofoil structure is designed such a way that the flow streamline is attached on the most of its surface like this. In this case, the problem is not with the pressure drag, the problem is with skin friction drag, because your wake is not that severe because the wake width you see compared to the bluff body, your wake is not that large as compared to your bluff body. So the drag acting on the aerofoil is mostly because of the skin friction. That is the shear stress term. Shear stress. If you see the shear stress term, tau is directly proportional to from the Newton's laws of viscosity. You can say that tau is proportional to dou u by dou y. Is u is the velocity. So if you have u velocity, if this gradient is low, right? If this gradient is low, you have less shear stress. If you have less shear stress, that means there is a less skin friction coefficient. That means less drag on the body. So to maintain less drag, laminar flow is better, which is having a less gradient. If you see the laminar boundary layer profile, this gradient considered at any position, this dou u by dou y is lesser than this sudden gradient. You see how much of velocity change in the turbulent boundary layer? This gradient. This is turbulent one, and this is laminar one. This is less than the turbulent. So the skin friction is less in the kind of laminar flow, and it helps to uh, decrease the skin friction drag or the on the aerofoil, which is not in the case of the bluff body. Uh, any queries still?
Okay, okay. Thank you.
Any more queries?
No, no, no. It's okay. Thank you.
Thank you. So now I think we can go to our problem solving session with
Sir,
no doubts.
last
Yes,
sir,
yes,
last
yes. Who is
question I
this?
have. Sir, Audit sir.
Arhit, yes, tell me.
Sir, this laminar boundary layer and this formation of pocket in airfoils. Sir, can you explain?
Laminar boundary layer is the pockets of
The pocket forming in the airfoil, sir, due to laminar boundary layer.
pocket forming, or you're talking about separation bubbles?
Yes, sir, separation bubble.
Separation bubbles we talk. Is it already discussed in the classes?
Yes, sir.
Like you are interested on it?
No, no, sir. It was discussed in the class. Sir, I could not understand this topic actually.
Okay. Suppose if you have a boundary layer like this, sorry, on the aerofoil, at low angle of attacks, the flow is able to sustain the adverse pressure gradient. If you want to better understand the adverse pressure gradient, I suggest you to always plot the pressure coefficient diagram on the surface. And it is looks like this. If you draw a pressure coefficient on along the chord line, suppose this is your chord line, I'm denoting with the X, and this is your CP. So it depends. It depends on what kind of aerofoil you are using. So I just a general profile of a CP distribution I drawn on the surface. And this is a CP distribution. You see at the very starting point of your leading edge, there is a sudden drop off. It should go to the negative level. This is a negative CP, and this is your very sudden drop of CP at the leading edge. This sudden drop of CP is because of high acceleration of fluid on the top surface. Because of this high acceleration, the fluid pressure at that point decreases very large. That means CP is uh, tending to more negative and negative. As it is going to very tending a negative and negative, and in the boundary layer, I'm talking about in the potential flow region. In this potential flow region means that is above the boundary layer. Suppose consider this is a laminar, very small region. This is a laminar boundary layer, and I'm talking about the potential flow region where your CP velocity is very high, but in the laminar boundary layer, your velocity is not that high because it is already zero, and your CP is very low. Here you will see suppose a free stream pressure or the local pressure at that point, and your velocity is here very low, and your CP, the local pressure is also very low. So to move the flow from this point to this point, though in the potential region it has the kinetic energy, it can move in this direction. But in the laminar region, I mean in the boundary layer region, it cannot move. I mean, I'm specifying at this point. At this point, it cannot move because it is already loss of kinetic energy, and the pressure at that point is also very low, because the pressure at that point is also due to the pressure in the potential region, that means above the boundary layer, is also very low. So the both things are uh, weak here, and it cannot take the help, I mean, cannot overcome this upstream pressure. That is what we say the adverse pressure. So this adverse pressure is not able to overcome, so it starts tends to separate at this point. The flow tends to separate at this point, and sometimes it cannot attach all the time, but there are specific conditions. There are how this flow can reattach, and sometimes it won't attach because of this um, bubble also. Like this is we call the laminar separation bubble. So because of this bubble, it will just because it is not able to overcome, it will separate from the surface and it will reattach only at certain conditions, which are like because of flow changing into the turbulent conditions, and or any use of active controls or passive controls of the suction surface, the flow can be reattached on the surface. We can manage this by using the control techniques, or maybe by forming the turbulent flow at this location by tripping, or also by using the boundary layer tripping. There are various techniques. So this laminar separation bubble generally forms on the surface. That means whatever the separated flow, separated does not mean that there is no flow in this region. There is a flow because it cannot take the air into the door, not a other fluid, cannot take any other fluid. Only matter should always present. It cannot be empty. So that means the flow is here is covered by this kind of structure. It's a kind of capsule, or it's a kind of bubble, where it is also in this also there is air present, but it cannot cross this boundary. It's stuck here. Whatever the content present inside this bubble, it always stuck here, and the remaining fluid will cross over the surface. That means this bubble is changing your camber or aerofoil shape, which changes if it is changing your camber or aerofoil shape, your CL or CD characteristics also vary. Suppose if it is going like this, your CL characteristics may vary like this. It decreases or again it increases. Anything can happen based upon the formation of the profile. So that is what we call as laminar separation bubble, or maybe I think the terminology described to you as a pocket. Is that what you asked, Arihit?
Yes, sir. Yes, sir. Got it.
Yeah, nice. So any more queries? Fine. So let us go to our next, sorry, problem solving session that we are trying to solve few problems regarding the discussion we have done so far. This also includes the past discussions. Yeah. The past lecture contents also are very necessary to solve the problems that you are doing in present assignment or the past assignment. So I believe this recapitulation of the concepts will help you to solve both the present problems or future assignment questions also. So please concentrate on the concepts I'm discussing here. And the first question is, which equations are essential for obtaining, let me show you the question, sorry. Yeah, this is our first question. Which equations are essential for obtaining the solution to an incompressible isothermal flow field? The question is stating two important conditions about the flow field. The details are if the flow field should be incompressible and flow field should be isothermal. The flow field is like satisfying both these conditions. We can only solve the flow field. Solve the flow field means we are solving the governing equations of it, like the simplified Navier-Stokes equations based upon these two conditions, or the simplified continuity equations. We can remove the, not remove, we can take out the density term from the continuity equation using the incompressibility condition, and we can neglect the temperature terms as the flow is isothermal. So if you neglect the energy equation, because we have, it is always stated that they're isothermal, so temperature effects are not there, so there is energy, no need to worry about the energy. And second law of thermodynamics is also not required, which includes the temperature terms. So mass conservation is always required for solving any kind of problems, and momentum conservation is also. These two are the basic necessary conditions for solving the flow field in this kind of characteristics. So this is the solution of this question. And the next thing is, next questions, there are two statements we have. The first one is statement one: in rotational flow, Bernoulli's equation is applicable only if the points of interest are located on the streamline. I can recall that we discussed these conditions or the assumptions that we use for the Bernoulli equation in the recapitulation of the, I mean, at the earlier stage of the lectures. And another condition is in rotational flow, Bernoulli equation is up. Sorry, in irrotational flow, Bernoulli equation is applicable everywhere in the flow field. If the flow field is irrotational, the Bernoulli equation is applicable at everywhere in the flow field. Yes, this statement is correct. In rotational flow, Bernoulli equation is applicable only if the points of interest are located on the streamline. Yes, both the statements are correct. Let's go to the next question. Okay. Here, which option is correct for the following statements? We are again having two statements, where the first statement is saying that in an inviscid incompressible flow, as the flow speed increases, so does the kinetic energy and dynamic pressure. We are having the conditions like inviscid and incompressible flow, and as the flow speed increases, so does the kinetic energy. Yes, kinetic energy is proportional to half, I mean, not proportional, it's proportional to the velocity. So kinetic energy K is half mv square. So kinetic energy also increases. The dynamic pressure, and dynamic pressure is just the kinetic energy per unit volume. So yes, the statement is again asking which option is correct for the following statement. This is correct, the first one. And the second statement is in a compressible flow, P naught minus Ps is equals to half rho v square, where v is the flow velocity, P naught is the stagnation pressure, and Ps is the pressure due to randomness in the molecules. The thing is, the question they are asking is about compressible flow. It is not incompressible flow. But the question, detail or the equation they given is Bernoulli equation, which is valid for the incompressible flow only. So the directly it is not acceptable or it's a false. Let's go to the next question. So in this question 4, we have, in order for flow to separate over an airfoil, we discussed this very extensively until now. So the flow must be in, like, the question is about for flow to separate over an airfoil, what is the required condition? The flow must be in favorable pressure gradient, the flow must be in adverse pressure gradient region, or the flow must be in neutral pressure gradient region. The thing we already know, the flow must be in adverse pressure gradient. And the next question is a problematic one, and the question stating that Miss Windy is standing in inviscid incompressible flow at a standard sea level conditions, given that rho equals to some value and P infinity equals to some value. Units also you can say these are all kg per meter cube, all are in same standards. We no need to convert these standards, where the airflow at speed of 50 meters per second. Okay, after walking along the seashore, at some distance, she felt the pressure decreased by 2.5% compared to her previous location. So she walked around a distance or some distance, did not mention how much distance it is, and she felt approximately a 2.5% decrease in the pressure. It should be noted clearly. And the question is asking us to find out what percentage she can feel the changes in air velocity at the new location. So it is a problematic one. Uh, let's start with basic given details. Okay. Okay. Let's write the given details. We have P infinity equals to 1.01 times 10 to the power 5 Newton per meter square, and rho infinity equals to 1.23 kg per meter cube, and V infinity equals to 50 meters per second, right? So we need to find that how much change in percentage in air velocity compared to the new location, and we also have incompressible flow inviscid. So we can directly use the Bernoulli equation. I always suggest you must note the conditions also, like whether it is incompressible flow or compressible flow or viscous or inviscid. If it's, those conditions are not properly stated, you should write or you should define by some current assumption, I mean, by some good logic, whether it is really applicable to Bernoulli flow or not, by using the given details. So, since they have given already these conditions, now let's directly use the Bernoulli equation, like that P infinity plus of rho V infinity square equals to P plus of rho V square. This is the Bernoulli equation for incompressible flow. Then we should define what are the parameters at what position that we are going to understand. The right hand side terms, that is P and V, these two terms are corresponding to the new location. Suppose this is the old location and this is the new location. The difference in pressure from old location to new location is 2.5%. We should use that to obtain the pressure difference from and the velocity difference from new location to old location. That means if the pressure difference is 2.5% means the change in pressure. This is an old location P infinity and this is a new location P. With respect to the old location, it is 2.5%. If you solve for this, you will get P equals to P infinity minus 2.5 by 100 times P infinity. Since you already have the P infinity value, that is P infinity equals to 1.01 times 10 to the power 5 Newton per meter square, you just substitute in that. Once you substitute, you will get the new location pressure value as P equals to 98475 Newton per meter square, right? Then now you have the pressure value at new location, pressure value at old location, and you don't have velocity at old and new location. But with the available values, let's substitute those values in this equation. Um, we have that P infinity equals to 1.01 times 10 to the power 5 plus half rho. This is V infinity square that we don't have, and then it is equals to P that we already just calculated, that is 98475. Let me write this. Yeah, that is 98475 times plus half rho V square. We already have the density also. The density won't change because it is already stated that incompressible flow. So 1.01 times 10 to the power 5 plus half, just substitute the density equals to 1.23. There is no rho infinity and rho because it is incompressible flow field. And then this is a new pressure. Then this, so we have only the two variables, that is V infinity and V. We have the unknowns here. To find that, let's use this equation. Like if you try to solve for, do we have the V? Yes, sorry. V also here that given as 50 meters per second. I did not see this, like, yeah, given condition is also as V infinity equals to 50 meters per second. So just substitute that 50 meters per second also V, like if you substitute that V infinity also as 50 meters per second, and let's try to solve for this. The equation becomes like the right hand side we have the unknown, that is V square. That unknown equals to 2 by rho times P infinity minus P plus 0.5 times rho V infinity square. So we have now the unknown in the left hand side and all the known terms in the right hand side. So just solve for this equation, that is 2 by 1.23 times 1.01 10 to the power 5 minus 98475. 98475 plus 50 square will give you 6605.69. If you do the square root of it, you will get V at the new location is 81.27 meters per second. But this is not the end of our question. We need to find the change in velocity. The change in velocity means change in velocity, I mean percentage change in velocity with respect to the old location. If you just substitute old velocity, sorry, new velocity value and old velocity value by old velocity equals to, you will get 62.54 percentage change. One important note is, can just observe the pressure difference. We have the pressure difference is that is, sorry, we have the pressure difference, that is P minus P infinity by P infinity into 100. The change in pressure is only 2.5 percentage, but the change in velocity, if you see, it is around 62 percentage. This is very interesting thing, like very for the small change in pressure, there's a 2.5 percentage, is not even significant. You have a velocity change of around 62.54 percentage, and this is what causes large hurricanes and environmental disaster kind of situations where the pressure drop is very low, but the velocity difference is very high. Why this is happening? Any other term is also responsible for it. This much, for this much of pressure difference, there is a large difference in velocity. Yes, one more parameter that is responsible is the density. For high density fluids like water, mercury, any other fluids, even though there is a very less pressure difference, the velocity difference is not very severe. But very less density fluids, like if you have air that is 1.23, you can see this much of velocity difference for a small change in the pressure. If it is, assume if it is a local pressure at the surroundings, you will feel a sudden high wind kind of situations. Okay, so this gives the solution of this question. And the next question is a two-dimensional density field we have here. In this two-dimensional density field, they stated that rho equals to 4x cube minus 2y square plus 4t. That is, x is a variable, y is a variable. Spatial parameters is already described as two-dimensional flow. But already, and additionally, there is one more parameter, that is t, that is indicating the time parameter. So it is highly unsteady kind of flow field and is associated with the velocity field. That is, velocity field is 3x square y I cap, that is u velocity, 2x y square j v velocity. the question stating that just determine the rate of change of density at point 3 comma 2 at time equals to 4. Here units are not mentioned, but we just assume that everything is in the same, not same, that the consistent units. So let's start our solution for this. The question is about rate of change of density. At the very beginning of the discussion, we already seen that how we can write a rate of change of a parameter in a substantial format, like it's based upon its convective local acceleration and the convective acceleration, that is d by dt equals to u dou by dou x plus v dou by dou y plus w dou by dou z plus dou by dou t. Whatever the parameter it is, we should substitute here. That is, suppose for our case it is density, so I will substitute it as density. Then now, since it is density and it is only two-dimensional, we are not going to consider this term. We just eliminate this, and the rate of change of density will be u dou rho by dou x plus v dou rho by dou y plus dou rho by dou t. Now we have u equals to, from the velocity field, u equals to 3x square y, v equals to 2xy square. Then yeah, these two are sufficient because we need only u and v. And then just substitute these things, and rho also we have. So sorry, let me substitute the details. Yeah, if I substitute the details, I have u equals to 3x square y, and then dou by dou x of 4x cube minus 2y square plus 40 plus v equals to 2xy square, and dou by dou y of 4x cube minus 2y square plus 40, and then plus dou by dou t of same rho value. I just write it as a row to save the space. If you simplify this, this is 3x square y times dou by dou x of this one will give you 3 times 4 x square plus 2xy square. If you simplify this one, it will give you minus 2 times 2 into y plus, if you substitute that rho value in the time parameter and simplify, it will give you value 4. Okay, now we have only the x and y values. We have that x equals to 2. I'm not going to simplify this, as this is a simple algebra problem, and x equals to 3, and y equals to 2, and time t equals to 4 units. They did not give the what exact units are, so we are dealing with units only. So just substitute these values in that equation, like upon the simplified format, the d rho by dt equals to 4 plus 36 x power 4 and y minus 8 xy cube. And now substitute in this, you will get the final solution as 5644 units. So this is the solution for this question. The substantial derivative, why we are doing the rate of change of, though they asked you the rate of change of density, it is a good example for one to understand what is the importance of substantial derivative. Let me physically show you what's happening here. Suppose this is your x and y field, and the density varying, you can assume that is varying in the third dimension, that is say in the z direction. And you have density, suppose at this point, just consider the density at this point is like 10 kg per meter cube, or 10 units. And if you change, if you assume that flow is steady, there is no unsteady kind of phenomena, then density changes from place to place, from here to here, suppose 12 units. This change in density in the spatial coordinates gives by these two convective parameters. This change in density in the flow field give you by these two. And density also changes. It cannot be 12 just based upon the xy plane. Density also changes with respect to time. Suppose this xy plane, consider it is at a 10th second. If you are going to see the density at 12th second, you're seeing the density at 12th second at the same x and y coordinates, you may get this is 9 kg per meter cube, sorry, and this is like say 14 kg per meter cube. Coordinates are same. Assume the coordinates are x1 and x2, or sorry, p1 and p2, the same points, but there is a change in density. This change in the density or the change in parameter with time will give you by this parameter. So that is why the rate of change of any parameter in the flow field constitute of both spatial parameter variation that we call as convective change, and another one is temporal change. Both combination we call as, or it is also called as local. Sometimes we say it is a local change, a local rate of change. Both combination we say it is a substantial derivative or a material derivative of that particular term. So that is how, that is why it is very important. If we get all the details, we need to see both in time parameter and the spatial parameter of the variable. Unless we don't see, it will give you all the clear information on that. Okay. Next question is about, we can see a wind tunnel here, a very large wind tunnel. Tests of the X-48 blended wing body configuration, courtesy NASA. And the question, let's read the question. An aeroplane model. In this aeroplane model, we have X-48 blended wing body. The wing body is X-48 blended wing body, which we can see is the aircraft, and housed in a subsonic wind tunnel. The wind tunnel is subsonic one. That is, the flow is less than the sound velocity. If the flow is more than the sound velocity, that is we call the supersonic velocity. If the flow is less than sound velocity, then we call it a subsonic velocity. And the wind tunnel nozzle has a contraction ratio of 12 to 1. So let's not worry about this, what is wind tunnel nozzle, but there is a contraction ratio of 12 to 1, that is saying that there is a change in area from uh, like if the section like where the velocity of this aircraft is placed, suppose here it is area is 1 unit, the free stream, like the upstream kind of thing, there is an area of in front of this uh, jet or in front of this aircraft, there is an area which is 12 times greater than the area surrounded by area surrounding this aircraft. So that is what we call as area ratio between the wind tunnel settling chamber and the test section. I hope wind tunnel, a basic level of introduction already given by the professor about what is this wind tunnel and its settling chamber and its test section. So I'm not going to details of it. If you are unaware of it, let me know. I will just give you one more introduction of what is this settling chamber and the test section. Are you comfortable with this wind tunnel settling chamber? Okay. If that is the case, let's continue with this question. The model has a wing platform of 0.50 meter square. That is the wing platform area. If you see this aircraft from top of this aircraft, that has area, if you calculate by integration of this around the boundaries of this aircraft, that is consist of 0.5 no, 50 meters square, which is significantly large. And then the aeroplane model's maximum lift coefficient is it can generate up to a maximum lift coefficient that we already aware of it. We've seen in past lectures what is the maximum lift coefficient of an aerofoil or an aircraft and how it is important for us. That is 1.37. The lift is measured using mechanical balance with a maximum force rating of 4,500 newtons. If the lift of airplane model exceeds 4,500 newtons, the balance will be breaked. During a given test of this airplane model, the plane is to turn the model through its whole range of angle of attack, including up to that for its maximum CL, and calculate the maximum pressure difference permissible between the wind tunnel settling chamber and the test section. So this is a lengthier question to read, but if we have a good exposure of the wind tunnel or how we test airfoils or aerodynamic object love for streamlined bodies, it is very easier to understand. It's like a simple kind of question. So I will just draw for your understanding how what is a wind tunnel and how the test section is and what are the parameters that they are describing here. A wind tunnel is more or less looks like if you see the any convergent divergent nozzle, it more or less looks like a convergent divergent nozzle, and this portion, this particular portion, this is your test section. There we place our model. I hope it is good to. This is where we place our model, and we used to have a kind of mechanism here. This is weight balance. This is a weight balance, and here is your settling chamber. Where the velocity is very low, almost considerable as a negligible low velocity, and your pressure is very high, that is total pressure. And this is your divergence section. Okay, so this is settling chamber, test section, and divergence section, and this is the convergent section. Now, a flow is happening over this aircraft. This is your testing object. We call it as object that we are going to test, or the specimen or testing object. This body we are going to test in this wind tunnel. Like instead of testing in the real-time experiments and real-time situations, very difficult. We create an environment like this, such that because of this contraction, like this contraction, they stated as this is 12 times. If it is this area means the cross-sectional area. If you see from the this side, if you see from this view, the area you see is this is 12 times this area. This is the test section area, right? So if it is 1 time, this inlet area is a 12 times. So that is what they given. That is a contraction ratio. And then this is your convergent section, because if you create any convergent zone like this, your fluid accelerates in this convergent zone as long as this convergent zone is present. And then accelerated fluid is now allowed to pass through this horizontal throat region or the test section region. Here the walls are so parallel, so your flow won't accelerate. It will accelerate up to this region, and the velocity after this is uniform velocity. Why we are creating such a uniform velocity means aircrafts fly at some altitudes in a uniform velocity. That means it's not like incoming flow is not happening in the real-time situation. We are creating the same in opposite way. by maintaining our aircraft steady and letting the flow come on top of it or ahead of it. It is like we are replicating the same situation by forcing the air at the same speed of aircraft that do in the real-time situations. But in the real-time situations, the flow speed is very high. To recreate the same situation, we use some non-dimensional kind of parameters, that is Reynolds number. This helps to recreate the same similarities of values. Like if the velocity of aircraft is 1,000 kilometers per hour in the real time, you no need to create the same velocity in the test section also. Based upon the Reynolds number and the flow you are using the density parameters, you can do the dynamic the similarity analysis, and you can apply low velocities, more or less low velocity curve compared to the real time situation. That comes with the dynamic similarity. To not deviate more from our topic, I'm not going to deal that. So now the free stream velocity is also, they did not describe how much of free stream velocity it is, but they gave that the plane form area, that is area if you see on top of the, from the top of the aircraft, you will see some area it is taking or it is covering. That area we call as plane form area, that is given as 0.5 meter square, right? So this is the overall view, and because of this incoming flow, the aircraft experience the drag force and the lift force. Both the drag force and lift force, airfoil, sorry, it's not
Sir, your
airfoil.
voice is not audible.
It's not audible. Hello?
Yes, sir. Now it is
Uh,
audible. Someone was
now
unmuted
it
and
is.
noise was coming.
Okay. So now this lift and drag is because of the flow distribution on the entire aircraft. This is not aerofoil. Please consider that this is an aircraft, and the characteristics are also more or less similar to an airfoil. And it has a maximum CL. It can reach up to the maximum CL lift coefficient up to 1.37. What is the CL definition is the lift value at that time instant by half rho V infinity square times the plane form area. This is S indicates the plane form area. This CL, it can reach a maximum of 1 point, how much they give? 1.37. This is a non-dimensional one. You can alter these dimensional quantities to get these non-dimensional things. So this is the entire test setup that an experimentalist generally do to test his airfoil or aircraft model, like how much of lift it is creating for the incoming flow, or how much high it can go, or many things they can calculate based upon from this test section that we always do as researchers uh, in any kind of institutes for their understanding of different flow physics on flow over a bodies. Now the question is, what is the permissible pressure difference? The pressure difference that we can allow between the wind tunnel settling chamber. This is your settling chamber. Suppose it is your P naught. Say it is a P naught, and this is a test section uh, test section's pressure. So I say it is the P. Yes, P is static pressure at the test section. So I do not like this. The question is how much of pressure that you can allow, that is difference in PS, P naught and PS. Then how to calculate that? It's a interesting thing to know, like it's a question given as a subsonic wind tunnel, whether I can apply the conditions of Bernoulli or not. That is the initial question that you will get. So let's see how you can apply. If you can apply the Bernoulli, how the solution will vary, and how much of pressure difference that you can create, that you should create to reach the maximum CL of 1.37. So let me write the given details of this question. The given details are like this. The contraction ratio between A, I will say this is A1 area at location 1, and this is area at location 2. A1 by A2 is equals to 12. Span area S equals to 0.50 meters square. CL max equals to 1.37. And maximum weight. Is it a maximum weight they given? Yeah, it's not a maximum weight, it's a maximum force rating is 4,500. That means this weight balance, it's a kind of, assume it is a kind of weighing machine that can sense a maximum value of 4,500 newtons. If 4,000, if it exceeds the 4,500 newtons, that weighing machine will damage. So we should limit our, this is the condition, we should limit our calculation such that weighing machine is only limited to 4,500, then what is the amount of pressure difference that we can create? And as I already discussed, that CL equals to L by half rho V infinity square S, and it is the maximum CL, CL max. CL max is like this, L max of rho infinity square S. If this is your condition, and the thing first you need to get is what is the velocity difference. If you can get the velocity at this particular location, that means at the area 2, if you can get the velocity at area 2, you can apply this velocity at area 1 as more or less 0, because you already set as this velocity is very insignificant, very less, because the pressure is very high and it's a very low velocity. So you can set the velocity at the saddle pressure is 0, and velocity at this particular zone is like we need to calculate that. From that velocity difference, if you use the Bernoulli equation, because we only learned so far with the Bernoulli, and assuming that velocity differences are not so significant, and we are applying just applying the Bernoulli. We are not aware of the theoreticals of high speed flow, like how pressure and velocity is coupled with a high speed flow. So let's applying this Bernoulli only. So we can apply the Bernoulli and we can get the pressure difference of P naught and Ps. But how to get the velocity at the section 2? If you want to get the velocity at the section 2, the details you have are from the CL max. From the CL max, they stated that you can reach only up to the CL max of 1.37, and you can reach up to the velocity, sorry, weight of 4,500 newtons. So now you have these two, that weight means the maximum lift that generates by this airfoil. If the airfoil is, so not airfoil, it's aircraft. If this aircraft is generating more than 4,500 newtons, that means the balance of this force sensor or this weighing machine cannot sense that more than that, or it will damage. So let's limit this lift also, because whatever the lift that generates by the this aircraft, it will sense by this weighing machine. So it should be limited by 4,500 newtons. And then CL max is 1.37 equals to 4,500 by half. We have density. Since we are going to use the Bernoulli equation, we should make our density also as a constant, and that is 1.23 kg per meter cube, already given to us. If the density is also stated as constant, and then what we left with, it is V infinity square. This is V infinity square, and then we have the surface area as, what is the surface area? How much? 0. Yeah, 0.50 meter square. Now we, this velocity is the velocity at the test section itself. This is the velocity. If you solve for this unknown, you will get the V infinity, or the velocity in the test section is 1.3, sorry, 103.35 meters per second. If you can recall our past lectures, if you substitute that CL max, that CL max indicates your velocity is as low as possible, that you can uh, the minimum velocity that required for the flight to fly with sustaining its weight. That means if aircraft is flying, means it has to balance its weight and lift. Suppose it's very important. Sorry. Suppose this is your lift creating by your aircraft, and this is your where is this? suppose this is your weight, that is self weight of this aircraft, or okay, this both should be balanced. If it is not balanced, the aircraft will fall down, or if it is lift is so high, the aircraft will continuously goes up. Both things may happen based if there is any force difference. So both things should be balanced. If suppose weight equals to lift, okay, now weight is equals to lift, and your aircraft needs to be balanced in such a way that at very low velocity I want to fly. That means if you don't have very high power, you cannot go at high velocity, like at the engine failure cases or some good cases. If you don't have a thrust, like if the engine is not working, you cannot not working properly, you cannot propel the aircraft with high velocity. So at that situation, what is the at least minimum required velocity that you need to maintain for your aircraft to maintain your aircraft at force balance of weight equals to lift? That means it either neither fall down neither goes up. So that lowest possible velocity, that means I definitely need to maintain the velocity of 103.35 meters per second to move my aircraft at that balancing of weight. Okay, so this is why we call as a stall velocity. If I reduce my velocity less than this, my aircraft will start falling down. If I increase the velocity more than this, I need to consume more fuel, and the lift will also goes up, and aircraft will move up. Okay, so this is the minimum velocity or stall velocity that we mentioned, that we terminologies. So very important and key aspect. Okay, now from the continuity, applying to the one-dimensional case, we already seen what is the continuity A1 V1 equals to A2 V2. We have the area ratio like A1 by A2 equals to, how much is the area ratio? 12 is to 1, that is I can say 12, such that I can get ratio of V2 by V1. If I transform this, reshuffle this above equation, you will get the V2 by V1 equals to the same. But you already have that V2 equals to, V2 means the velocity in the test section. We just obtained that. That is V2 equals to 103.35 meters per second. From this, you can obtain V1 equals to, if you simplify that, you will get some. Shall we solve for this? I think I did not mention that V1 equation here. V1 value, yes. One more good way of doing this, you can directly solve for the V1 here, and you can apply this V1 value, because as you have already V2 by V1 equals to 12, just solve for the V1, and as you know, pressure difference is the one we need to calculate, that is P naught minus PS. It is equals to uh, half rho difference in velocity. This is what you will get. This is not V infinity, this is V infinity minus V naught, V1 I can say, or V naught of V1. This is what you, sorry, this is individual's case. If you simplify the Bernoulli equation, they asked only for the pressure difference. So you can solve the velocity from here, that is V naught, that is yes, that is V naught, velocity in the test section. That is also V naught equals to V1, don't get confused. V naught equals to V1, solve for the V1 as V2 by V1 equals to 12, and just substitute in this, so that you will get, you already have V infinity as 103.35, V1 you can get from this, and density they already given as 1.23 kg per meter square. And simply if you substitute, they only asked for the pressure difference, you will get the P naught minus PS. But one important uh, simplification of Bernoulli equation that you can use for later on session also, I wrote here, which is helpful for you. Our question is already solved, but one more method, I am just substituting these continuity equation, Bernoulli equation, and I will couple it, so that later on sessions you can use it. So I will discuss that. Uh, Suppose your Bernoulli equation is like this: P1 plus half rho V1 square is equals to P2 plus half rho V2 square. This is your Bernoulli equation. Let's simplify this Bernoulli equation for V2, that is velocity in the second point. V2 square equals to 2 by rho P1 minus P2 plus V1 square. If you simplify for this equation for V2 square, now V2 square is equals to, I can write like this. I will directly write and I will show you how, why and why, how can one can write like this format: A2 by A1 square B2 square. How I can write this means we have A1 V1 equals to A2 V2. We already discussed this. And here we have V1. If you solve for V1, what it will show? A2 by A1 times V2. But we have V1 square, so just substitute the square of it. So I just substitute that continuity equation. Now we have A2 by A1 equals to 12. That is a contraction ratio. I will say it as some constant. So whenever if you see any contraction ratio in your problems, it is very good to write in this format. You can just directly substitute that A2 by A1 equals to 12. And they just ask for only for the pressure difference again. You know the density. So only the unknowns are the V2. It's the left and right hand terms. So the pressure difference is can be written like this: of rho V2 square times 1 minus A2 by A1 square. Sometimes it is also, it can be in questions, you can also find like this: the pressure difference and dynamic, like the density and velocity will be given at the test section. They will ask you the for the pressure difference, and they may ask you for the contraction ratio also. So this equation is will be very helpful for you whenever you try to solve this kind of wind tunnel problems or the convergent divergent section kind of problems. This can also be useful for uh, if you are solving only the problems that deals with one-dimensional studies, because it is already clearly stated that we are using the one-dimensional continuity equation. So directly you can relate that. If you know a flow like this and you have a velocity here v2, and the flow is governing by this kind of wall, and you need to find out the pressure difference at this point, this is the pressure difference at P0 and pressure difference at P2, and I want the pressure difference between these 2 points. You have the velocity here, area here, and you can just directly substitute using this equation. You don't need to uh, start from the entire thing that we have solved from the from starting of this question. Okay. So after upon solving, like we have all these values, like V2 we have, and rho density we have, V2 by contraction ratio also we have. Once you solve it, you will get the pressure difference as P1 minus P2 equals to 6503.26 Newton per meter square. After substituting all the known values, you will get this pressure difference. So it is a key term that a beautifully coupled that Bernoulli equation with continuity equation. The both are very good for the one-dimensional kind of situations. Okay, let's go to the next solution. And before going to the next solution, I just want to take any couple of questions. We are already having just 8 more minutes for the today's session. Any questions, quickly? Am I audible?
Yes, sir.
Okay. Any questions? Okay. If no questions, let's quickly see one more uh, short question in this session. This I will take time to explain this. It is also important one, which I will take time. But let's see this question. asking about the fact included in the statements. We have been solving these kind of questions from the long. The question is, which option is correct for the following statements? The statement one, for high-speed fluid flow over a flat plate, the boundary layer shows compressible behavior, and as a result, you will note that it is a high-speed flow, and the boundary layer shows compressible behavior. Yes, and as a result, very small amount of kinetic energy is dissipated within the boundary layer by the time velocity reaches zero at the wall. This we already discussed. The question stating that the flow is very high. I mean, flow speed, no, flow speed is very high, and the flow speed, that much of speed should reach. Suppose if it is your boundary layer, if it is having in the free stream, it is 340 meters per second, that should reach to zero on the boundary. This much of velocity difference, that is 340 to zero, and it should reach to very small thickness. It should reach in the very small thickness, that is boundary layer thickness. You can say 5 mm, less than 10 mm also sometimes you can observe. MMs is also still large value. So in that small region, this much of energy is going to be uh, suddenly as a zero. How it is possible? That means a lot of kinetic energy should be conserved. So the thing they are stating is a very small amount of energy is dissipated. Is it possible? No. So this statement is false because a large amount of energy is dissipated in the boundary layer, and that it will convert to internal energy. There, the internal energy converts into the temperature. That's how the energy is conserved. Like it will amount the kinetic energy is going to convert into the thermal energy. Next, the second statement is boundary layer theory was proposed based on order of magnitude analysis of Navier-Stokes equation where small magnitude terms are neglected. Yes, if you have understood that concepts in the classes, that you can easily see that to start the boundary layer uh, analysis, we need to neglect so many terms like velocity gradients and velocity difference along the x and velocity in the y direction. Everything here, whatever the in the order of sense, like if something is 10 times less than, or something is 100 times less than the value that we are having now, then we are neglecting those kind of values, and we are simplifying for our purpose. So it will lose the accuracy of the solution. We may not get the exact one, but it will give you some insights of the solution. Okay, so that is this is the question solution of this question. And the final question, we are having two more questions left, but we'll discuss those two questions in the next week. And in this question, the displacement thickness is defined as the distance by which the external flow is displaced. External flow is displaced dash due to dash in which the boundary dash due to dash in velocity within the boundary layer. We are asking that displacement thickness is defined as the distance by which external dash flow. That means externally we have the potential flow. Viscous flow is not the displacement one because the displacement thickness is related to the mass conservation. So it is the distance in the potential flow that is displaced outwards or inwards, displaced above, like it won't come into the viscous region. The potential region moves out of the viscous region due to decrease of velocity within the boundary layer. So this is the solution. If you are not clear with this statement, I will give you the details of it in the next class. So let me take any quick questions so far. Or then we can wind up the session. Okay, if no questions, I would like to thank everyone for joining this session, and I hope you all joined and clarified your doubts in the live session by Professor Arnav Roy sir also. So maybe if you are still doubts, you can post in the Google form, sorry, Google Documents. You can post there, and we will respond your question. Okay. So thank you all. Okay, I will see you all in the next week. Any questions? If not, we can leave this meeting. Okay.
No question, sir.
Okay. Thank you. See you next week. Post your queries in the
Thank
document.
you, sir.
Yeah.
Okay, sir.